A metric space is compact if and only if it is countably compact. From the definition itself, it is obvious that compactness always implies countable compactness. It does not depend on the fact that the space is metrizable or not. For the converse part, we already know that every countably compact metric space, second countable, and hence Lindelof. We know that every second countable space is a Lindelof. Our space will be Lindelof. But we know that countable compactness together with Lindelof property implies compactness, because Lindelof property says that every cover has a countable subcover, and being countably compact implies that every countable open cover will have a finite subcover. So these two properties together will definitely ensure that every open cover will have a finite subcover. That means the space will be compact. Therefore, we can conclude that every countably compact metric space is compact. This completes the proof of the converse part of our result. Proposition: every continuous real valued function on a countably compact space is bounded and attains its extrema. Let us consider a function, say f from x to r, which is continuous, and suppose that the space X is a countably compact space. Since countable compactness is preserved under continuous functions, the image of x under the continuous function f, that is f of x, will be countably compact. But f of x is a subspace of R, which is a metrizable space. Since metrizability is hereditary, the subspace f of x is also metrizable. That is, we can regard f of x as a metric space. Therefore, we can see that f of x is a countably compact metric space. And this will imply that f of x is compact, since we know that a metric space is compact if and only if it is countably compact using the previous result. So the range of f of x is compact, and f of x is a subset of R. Since f of x is a compact subset of R, it will be bounded. We also know that every compact subset of R will contain both its supremum and infimum, as it is also closed. Therefore, we can conclude that f of x is bounded and attains its extrema. That is, we can conclude that the function f is bounded and attains its extrema, thus arriving at the desired conclusion about the given function f. So we can conclude that every continuous real valued function on a countably compact space is bounded and attains its extrema.